three bodies, identical masses, moving under nothing but gravity, and yet they trace this exact path repeatedly forever. This is the figure 8 orbit. It was proven to exist mathematically in the year 2000, and this simulator computes it in real time in MATLAB. Given n masses in space, each pulling each other through Newton's law of gravity, predict where they go. For two bodies, there is an exact formula. For three or more bodies, there isn't. The motion is generally chaotic. The only way to study it is to simulate it numerically, step by step, which is exactly what this app does. The interface has three columns. On the left is the control panel. At the top is the preset selector. 16 configurations ranging from classical choreographics to polygon formations to galaxy scale systems. Below that, when auto-configure is unchecked, you can manually tune the gravitational constant g, the time step dt, the steps per tick, and the body radius. Auto-configure logs these to optimal values for each preset, so everything looks correct out of the box. Below the physics controls are the collision settings. You can enable body collisions with either elastic or inelastic options. The center is the simulation viewport. The camera auto-zooms every 10 steps to keep all bodies visible. On the right, the top section shows a description of the selected preset. The bottom is the energy visualizer, where we can see the kinetic energy, potential energy, and the total energy curves. Let me explain what is actually happening under the hood. Every simulation tick, the app computes gravitational acceleration on every body from every other body's perspective simultaneously. Instead of nested loops, this is done using a single vectorized matrix operation. The x and y distances between all n bodies are computed as n by n matrices using MATLAB broadcasting. The gravitational factor, which involves 1 over r cubed, not r squared, because we need the vector direction, is computed directly from squared distance without ever calling square root, which is an expensive method. Then, a single matrix multiply and row sum gives accelerations for all n bodies at once. Once we have accelerations, the positions and velocities are updated using the velocity Verlet method. This is a symplectic integrator. It doesn't just approximate the equations of motion. It preserves a mathematical quantity called the shadow Hamiltonian. In practice, this means the total energy stays bounded rather than drifting away over time. You can see this directly here. The red line is the kinetic energy, the blue is the potential energy. They oscillate as bodies speed up and down, but the green total energy line stays flat. The flatness is the proof that the integrator is working correctly. The app can record and export the simulation as an MP4 video. You can check export before running, choose quality and FPS, run the simulation, and then hit stop. The renderer replaces every recorded frame with the same camera tracking as the live simulation, shows estimated time remaining, and saves the file to the project folder. You can press escape at any time while rendering to cancel it. Note that rendering longer simulations can take a while. Let me show you the core of the simulator, about 10 lines of MATLAB that compute gravity for all n bodies simultaneously. Here the acceleration is computed in N-body ACC function, or the N-body acceleration function. Here we calculate the r squared distance and add a simple softening factor so that the bodies that are too close don't produce division by 0. Again, we calculate the inverse r cube method from the property r squared to the power minus 1.5. Here, while calculating the inverse r cube, we skip the square root function, because it's pretty expensive to do every frame. Instead, we do this, and this is the integrator. Here we call N-body ACC twice. These three lines, half tick, full drift, half tick. Acceleration is evaluated twice per step, once before and once after the position update. That 2-point evaluation is what makes it symplectic and energy conserving, and its result is a flat green line in the energy visualizer. This simulator uses the same mathematical foundation as molecular dynamics, pairwise interactions, and numerical integrations, energy conservation, and its monitoring. The velocity Verlet integrator we implemented here is widely known and implemented in many other simulators. The N-body problem taught us that deterministic systems governed by well-understood physics can still produce extraordinarily complex behavior, and a principle that appears throughout engineering from fluid turbulence to reaction kinetics. Thank you.